Okay, this is the pre-video for section 5.4. I have posted new notes for this. Notice at the top up here it says they are updated. Those are in the same section with the original 5.4 notes. I did this to cover this in an order that I could do the pre-video all together, and then we'll pick up in class. We'll just go from there. So I tried to keep the easier problems all at the beginning. So an exponential function, remember, was f of x equals a to the x. That's what we've spent the last two class sessions covering. And we noticed that it was a one-to-one function because it passed, so just making sure you realize what we're talking about here. One-to-one, the functions we've just been graphing. So a to the x, all of those graph in a way that they look like this. And they are one-to-one because they pass the vertical line test and the horizontal line test. So because it's one-to-one, it has an inverse. The inverse of an exponential function is called a logarithm function. It has the same base as the original exponential. And here's what's really going on here. If you write y equals a to the x and you go to swap, you get x equals a to the y. And you think, how do I solve that for y? Well, they decided that you could do this by finding a bunch of numbers that are approximately what you're looking at, and you kind of came up with these tables, and they were really complicated to use. Log tables are fun, but not really what everybody wants to do since there's a log button on your calculator now. So they decided to take this and use the power of calculators to help us by writing this in a different way. So what we call it is y equals log base a of x. Notice that this exponent up here is now solved for y, so it's solved for itself. This is still the base, but it's called a log, and this is called the argument. So this guy right here is called the argument of the log, and this is the base of the original, and this was the exponent of the inverse. And this is how we work with it. Now, so what we're learning today on this pre-video is just how to convert an exponential function into a log and backwards, and then we'll do some very simple computations with that. Some things to note. The domain of an exponential was all real numbers, and its range was, remember, if it's not moved any, it's greater than 0, so 0 to infinity. So that means that an exponential function that has been swapped to its inverse, which means now it's a log, is going to have a domain of 0 to infinity and a range of negative infinity to infinity. Remember, the domain and range swap in an inverse. So where we never had a domain restriction with exponentials, we do have domain restrictions with logs, and they have to be that the argument stays greater than 0. So that's going to be really important. Anytime we go to solve an equation, we're going to have to say, ooh, does this work? And does it give us all of our logs having their arguments greater than 0? So that'll be really important for class. So I'll show you that. Okay, so the way we convert between exponential and logarithm form is that, and I like to think of this as there's an easy way to go and there's the harder way. It is super easy to take a log and change it into an exponent. People usually have more trouble with going from exponential to log. So let me show you an easy example of how to take a log and to go to exponential. So log 3 of x equals, let's say, 7. Okay, so when we do the log technique, I like to do something called the spiral. So if I'm going from a log to an exponential, you start with your base, you go over and grab your exponent, and you say it's equal to the argument. So this reads as 3 to the 7th equals x. So that's called the spiral. Base to the other side is the exponent, back across is the equal to part. So 3 to the 7th power equals x. And notice that when you turned it into this, now you can solve it. So this is the reason we want to go between the two forms, so that we can solve problems that don't make sense in certain situations. If we want to go from an exponential to a log, there's a little bit more involved. So say I wanted to do 3 to the x equals 5th. I don't know what you would raise 3 to make 5, because 3 to the first is 3. 3 squared is 9. So it's something between 1 and 2. It's going to be some kind of decimal. Well, if we take the log format, it's always log, and then a base, and then an argument, and then something on the other side. The base is still the base. The exponent on the base is the answer. The part that's over here by itself is the argument. So 3 to what power? So you can still see this from the spiral. 3 to what power equals 5? And if you have a calculator, we're going to show you how then you could solve this, because there's a way to solve. Our calculator will solve this for us if we know how to enter it in correctly. And if we do, then we'll be able to know what x is. It's going to be 1 point something. So this will open up a whole bunch more equations that we can solve. We were never able to solve 3 to the x equals 5th before, or equals 5 before, because we couldn't use our rule that they couldn't have the same base. The only other rule we knew about exponents was if they had the same base on each side, the exponents were equal. Well, that's no longer going to help us when the bases don't match. So this is going to be how we solve those. We will convert them to logarithms. So that's the big gist of what's the most important thing you need from the pre-video. It's how to convert back and forth. So we're going to do a bunch of examples. Here's a preset of examples right here, but I'm going to do these down here. So let's change this to log form. So when we're going to log form, remember you write log blank blank equals blank. Okay, so the base that has the exponent attached to it is the base of your log. The actual exponent is the equal to part. The part that's by itself is the argument. So notice this is now can be rewritten a little bit cleaner as log 3 of 243 equals x. This one is also going to be log 3, and then on the other side there'll be a negative 4, and the argument is the 1 over 81. This one has all letters but still follow the same pattern. It's log of the part that has the exponent is c, so that's our base. The exponent goes on the other side, so that's p. The argument is what's left, so it's the d. For this one, we would have log base 7, since 7 has an exponent attached to it. X is going to be on the other side since it is the exponent. And there's actually two things here. These are both part of my argument, so 100p. This one would be log base 3, the exponent is negative 2x, and the argument is this fraction, p over f. So they don't always have to look nice, but this is just how do you convert it. And then this one, the base is, because here's the exponent, the base is 0.9. The exponent was t, and the 1/2 is the argument. So that is 6 different ones where we've practiced converting from exponential form to log form. Example 2 is actually the easier way because this is where you can just do your spiral. If you're going from log to exponential, it's just 3 to the 4th equals 81. 4 to the negative 5th equals 1 over 243. V to the q equals w. 6 to the 3rd equals the argument, which is 2x minus 1. Notice now I could solve that. I could cube 6, add 1, and then divide by 2. For this one, it would be 4. Now this time the exponent is, it's a binomial, so 5 minus x equals p. And a to the 3/4 equals 343. So notice you're just practicing converting. So not much going on, just learning how to go back and forth. That's actually one of the most important skills in section 5.4. Okay, the only other thing I want to do on the pre-video, because I tried to keep this short as possible, is common logs and natural logs. These are the two that show up on your actual calculator. So I can't physically do log 3 of 5 on the calculator that specific way unless I have a calculator that does different bases than 10 or e. The calculators most of the time only do base 10 and base e. So later on, and this will come on with Thursday's section, it'll be some of Tuesday or Monday, possibly Wednesday or Thursday, depending on which class you're in. But we have to learn how to convert non-base 10s and e's to something our calculator can do. So we will teach you that. But for right now, we want to introduce the two that are actually on your calculator. So if you just see log x, or just log, so you see the button log on your calculator, this is understood to be base 10. We don't write log base 10. Sometimes I will, just to emphasize, but normally answers don't have log base 10. They just say log. So the log button on your calculator only works when you're dealing with base 10. E to the x was our other really nice, fun base that we learned about in section 5.3. This one can be turned into a log as well, but it's called the natural logarithm. So we use a symbol ln of x. So ln is actually a shortened version of log base e. So it's understood that this is a base e. So that's the two special ones. So here's some things that are true about logs in general. Anytime you have 0 as the answer to a log, that says this base to the 0 power, and that's a 1. So what we know now is if your argument's ever just the number 1, the answer is going to be 0. If the base inside here and the argument base match, the answer is always the exponent. So in this scenario, I know it's kind of hard to see, that's a base 1. A to what power equals a to the first? Well, it have to be to the first power. A to what power equals a to the x? It's going to be x. Here's another version of that. They have a log a of x, where log a is the exponent. If those bases match, the answer is just the x. So these are just some special properties that are true for logs. Now this says change this to a log. Okay, so remember, same thing as before. Log base 10, answer on the other side is 4, and this is the argument of 10,000. This would be, now I wouldn't leave that as log base 10, so I wanted to show you that's how we did it before, but we would write it as just log of 10,000 equals 4, because it's understood that the 10 is there if you don't write it. And I believe this is how WebAssign and it wants you to write it, and I prefer you not to write the base 10 too. If you did, I wouldn't be too angry, but we like to realize that log base 10 is just log. So this one would be just log. Since it's a base 10, the answer over on the other side is the exponent, and the argument is the 0.01. This next one, we have log of 10 again, so that'll just be log. The answer is the x, and this is 38z for the argument. This one would be log base e, which I'm going to convert in just a minute. The exponent is 4, and the argument is the d. So we don't leave it like this. We write natural log of d equals 4. So notice log base e is written as ln. And this one would again be ln, since it's a e. The answer on the other side is the 0.1 t, and on this side we have the argument of x plus 2. So these should be a little bit easier because the next example is just showing you how to convert these back to being exponentials. So notice there's a base 10 here understood. So that would be 10 to the negative 8 equals x, which we could then solve if we wanted. This is also understood to be base 10. So 10 to the y minus 2 equals x. This is base e, because notice it's natural log. So e to the 1/2 equals x. We could solve that with our calculator. This would be e to the 7 plus x equals z. And this is also base e, so e to the 1.2 equals t minus 5. So notice just by switching these to the other format, some of these are able to be solved just using your calculator. And I'm going to do one more. This is the same property that was up above. I copied it twice. So we're going to do these, and we're going to use our ability to change the format to answer the question. So it says find the number if possible. If that means that you're kind of missing the equal to part. So if you want, you can call all of these equal to x. That just gives you something to use to do the conversion. So this would be 8 to the x equals 1. Anything to what power equals 1? That would mean x has to be 0. So 8 to the 0 equals 1. This says 9 to the x equals 9. So notice bases are the same, so the exponent has to be the same as this side, so it's a 1. 5 to the x equals 0. This is not possible. You can't raise anything to a power and get 0, because even at 5 to the 0 is not 0, it's 1. So this one's not possible. 6 to the, oops, I don't know why that's an E. 6 to the x, so we're doing our spiral here. I'm not writing it each time, but we're doing our spiral. So 6 to the x equals 6 to the 7th, so x has to equal 7. Now these are a little bit harder because they're not the same format. So notice this, I'm just going to use the property. The 5 and the 5 match. That means x equals 4. That's using that property up above, that if the bases match, the answer is the other number. For this one, this would be 3 to the x, using our spiral, equals 243. And this one would be 2 to the x equals 128. Now notice, these bases don't match, but maybe we can reduce it down so that they do. So let's just look at 3. 3 to the 4th power is 81. 3 to the 5th power is 243. So this guy can be written as 3 to the x equals 3 to the 5th, so x equals 5. And I believe 128 is also 2 to some power. 2 to the 5th is 32. 2 to the 6th is 64. Maybe it's 2 to the 7th. Yep. So this is 2 to the 7th. So that means x equals 7 since the bases match. All right. So I'm going to go back through and circle all those answers. So the first answer was x equals 0, then x equals 1, then not possible, x equals 7, x equals 4, then 5 and 7. All right, last one for the pre-video. That will leave us with graphing and solving equations on our next class session. So this is, again, recognizing the property. Notice there's no base here. That means it's either one of our special ones, so it's base 10. So the bases match, the answer is just the other number. Again, the bases match. The base isn't written here, but it's log. So this is 10 and 10, so the answer is the other number. This one's a little trickier. You might want to use an x over here. So this is 10 to the x equals 100,000. So we need to think, is 100,000 10 to a power? So 10 to the 3rd is 1,000. 10 to the 4th is 10,000, so I bet it's 10 to the 5th. Yep. So this is 10 to the 5th, so since the bases match, the answer is just the exponent. This is also base 10, and we can think of it as being equal to x. 10 to the x equals 0.001. Okay, that doesn't look as good, but 1 divided by 10 is 0.1. 1 divided by 10 squared is 0.01. 1 divided by 10 cubed is this. So this is actually 1 over 10 cubed. Now the 10s match, but there's not in the right place. So remember, we learned that if we move this, we have to change the sign of the exponent. So that would be 10 to the negative 3. So it looks like x equals negative 3. This, the bases match. It's natural log, so e and e, so the answer is just 8. Natural log is base e, so the bases match, so it's 2/3. So that is pretty much where I wanted to stop with the pre-video. So you'll see a lot more of these little pieces that we've been doing as we work through more problems, but the big fact here that you have to get is that you need to know how to convert a log to an exponential and an exponential to a log. If you can do those two things, you can usually answer 90% of the questions in these sections. Now what we'll do in class is we'll finish up some graphs of logs and some simple equations, and then the last two sections, 5.5 and 5.6, are pretty much identical to each other. So we'll start covering that in class next time as well, but we'll probably have to finish it up at the beginning of the next class session. So we're going to be looking at properties of logs and how that helps us solve harder equations. So that is it for today.